Uh, good afternoon, everyone. Can you guys confirm if you guys are hearing me clearly?
Yes, sir.
Okay, so I want to welcome everyone to my lecture today. Today, November 11, 2020. I'm actually going to be walking you through another exciting topic in statistics. And of course, we are still on the probability distribution of continuous random variable. Only that today we actually want to finish this topic. And of course, the midtime is around the corner, and you know, uh, information about how the midtime is actually going to be. Of course, I'm going to give you that in the next lecture. Okay, so like I said, I want to welcome you to my lecture today. I'm still going to be discussing on probability distribution of continuous random variable, and we're going to have a quick review on Weibull distribution. The other time we actually uh, work on Weibull distribution. Then I'm going to also show you how you can do that in R. Then we're going to talk about gamma distribution, the beta distribution, then how to do that in R. So I'm actually going to walk you through all that. Now, when I give you a question to do, of course, you are comfortable to use whatever method you want to use. Okay. So because at times when you use when you are not comfortable with using the manual approach, there's no problem. You can use that is the essence of the software. But you know what? I'm going to walk you through that today. Now I introduced you to Weibull distribution the other time, and I described this distribution to be one of the to be in a family of continuous probability distribution. And this distribution perform a lot of function, okay? And it can be used to model most of real life practical situation. I said it can be used to model the waiting time before the occurrence of an event. An example of such, you can actually use this distribution to actually, we use it in survival analysis, we use it in reliability study, okay? So how many time am I going to wait? How long am I going to wait before certain event occur and stuff like that? And of course, in insurance company, this can also be used because you may want to find the probability of reinsurance size. If you have a good number of people that insure, or that have a claim, I mean the insurance claim, that have a claim right now, how long are we going to wait before, and another set of people that they have insurance claim before are going to have the claim again. Okay, so because it is not something that we expect that you occur frequently. So like I said, the Weibull distribution is a very good distribution to handle that. Now, what I'm showing you on my screen right now is the probability distribution of a Weibull distribution. It has two parameters, alpha and beta. Alpha is the shape and beta is the scale, okay? And the two parameters are non-negative, okay? And of course, the other time I give you the mean and variance. Like for instance, if I want to calculate the waiting time the average waiting time of a particular of the occurrence of a particular event. Or do you know that the moment I know the two parameters I'm actually going to that can be determined? Okay, I mentioned uh, insurance company right now they want to determine the size of reinsurance claim. Okay, reinsurance claim. Okay, maybe they want to determine the size. Okay, the size of reinsurance claim. When I say reinsurance claim, okay. So and of course, Weibull distribution can be used in that regard. Okay, so if I want to know the mean, if I want to know the average number of time I'm actually going to wait, before that can happen, then I need to make use of the mean of a Weibull distribution. which is this guy here. And of course, this can be computed in R. Okay. I told you the other time, if you take a look at this sign, that is gamma. Okay. In R, we call that gamma. If the moment you just write gamma, you're done. So if I'm going to get gamma 5, okay, it's just going to be gamma. You're going to write gamma into 5. Okay. Simply, you're going to have it computed. Okay. And of course, I put the variance. Okay. I put the variance for that. This is the formula to find the variance. There's something that I want to take note. The mean and the variance, they are in terms of the parameters. Okay, they are in terms of the parameters. Take a look at that. Okay, so now let me tell you this. Do you remember on Monday I walked you through the manual way uh, to do that? But today I'm going to show you how to use R. Using the R is very, very easy. Okay, very, very easy if you make use of the R. Now take a look at this. So, for example, let's say X, this one means X follows a Weibull distribution with parameter 3 and 5. Let me tell you the Weibull is this, Weibull, okay, with parameter alpha and beta. So it means your alpha equal to 3 here, your beta equal to 5. Take a look at that. Alpha comes before beta. Here it means alpha equal to 3, beta equal to 5. Okay, alpha is the shape parameter and beta is the scale. Okay, now you want to find the probability of S greater than 7. Okay, you remember the other time, if you want to find it, if you want to do that manually, okay, that may be computationally intensive. Now, if you want to find the probability of S greater than 7, you're going to do 1 minus probability of X less or equal to 7, which is then 1 minus CDF at 0.7. And of course, you remember what I gave you the other time as the CDF for Weibull distribution is 1 minus exponential raised to power minus x over beta raised to power alpha. You remember that is the formula you're going to use if you want to get the CDF. And after getting, this formula right here is the same thing as this. Give me 1 second. Uh, yeah, this formula right here is the same thing as big F of x. Okay, you just need to plug in the value of 7 and your alpha and beta. Okay, don't forget there's alpha here. Okay, now that is how to do that manually. But if you want to do that using the how, so easy, guys, so easy. Take a look at this. Oh my God, that is a simple code. Simple code. 1 minus p Weibull. In R. Okay, the p Weibull. This guy here. Give me 1 second. This guy here. This guy here is what we use to compute the CDF for Weibull. Now it means I want to compute the CDF for Weibull at S equal to 7, okay? And the parameters, that's a 5 and 3. The shape parameter, alpha equal to, you look at the shape parameter,
Excuse
uh,
me, Professor.
okay, yeah, go ahead.
Um, isn't the shapes parameter is the alpha?
Okay, you are very, actually, what happened is this. you know, if I give you something like this, I said the other time that the first one is going to be alpha, the second one is going to be beta. At times we could also write it beta comma alpha, but you know what? An examiner is going to tell you what is the alpha, what is the beta, because there are some textbook that you're actually going to see this. Does that make sense to you now?
Okay. But for
Yeah.
this one, we are using beta alpha, right?
Yeah. So here we are using the shape. The shape equal to 5 and scale equal to 3 means here your shape alpha is 5, beta is 3. Does that make sense?
Yes, yes. Thank you.
Okay, so like I said, the examiner is going to tell you uh, which one is going to be the shape and which one is going to be the scale. Or the only thing you just need to do, you need to be able to state that in the code like that. Shape equal to 5, scale equal to whatever you are given. Now, do you know that if you just compute this one alone, that is the probability of S less or equal to 7. just this one here. That is the probability of x less or equal to 7. Then you are subtracting that from 1, then it means you are doing the probability of x greater than 7. Can you see that now? That's so easy to do with the R. Okay. Now, the next one now, take a look at this one here. Okay. Uh, in a situation where I give you something like this, where I did not really specify which one is alpha, which one is beta, I want you to always take the first one here as alpha and the second one as beta. Okay. When I put it like that and I don't really state which one is alpha, which one is beta, please always act so. Now, I believe with what you have done now, you'll be able to, you know how to find this, you know how to find this. Okay. You know how to find this. Now, somebody said, can we use R to calculate the expected value of X? Yes. You know, the expected value of X is beta into gamma 1 plus 1 over alpha. If I want to do this in R, what am I going to do? Well, I'm just going to write beta star gamma gamma, okay, into 1 plus 1 over alpha. Look at that. That is the coding now. I'm just going to plug in the value. What is beta? And I'm going to plug in the value of alpha. The R will automatically compute that for me. Okay. And you're going to do the same thing to the variance. Okay. You can actually use, but only that you need to code that directly. There's no direct code. I mean, there is no short code for that. You only need to do what I said, just going to program the formula. Okay. Now that's all about about Weibull distribution. Now let me come to gamma distribution. A gamma distribution, of course, is another distribution for modeling waiting time. It performs the same function as Weibull. In fact, it has two parameters, alpha and beta, and the same, alpha represents shape, beta represents scale. And you know what? We use gamma distribution to determine the amount of rainfall. We also use it to model extreme events. Okay. I don't know whether you guys have heard about extreme value theory. Okay, like the event of earthquake, hurricane, and so on like that. Okay, so gamma distribution can be used to model the occurrence of that. Like if you call now, how long are we going to wait? Of course, before the occurrence of another one. And do you know that the flow of items through manufacturing to distribution process also follow gamma distribution? That's a good news now in the world uh, on COVID. A particular company has come out, FISA has come out to say, uh, you know, uh, that their vaccine actually cure COVID and it has more than 90% efficiency. Now, the further remain if they're into production now, the time, between production and distribution process, because one thing is to produce, another thing is distribution. Okay, so and the people have been curious about what the distribution, I mean, when is the distribution of the vaccine is going to be. Now, what I'm trying to tell you right now, the gamma distribution can actually be used to determine the waiting time between production, and the distribution process. Okay. Now, I don't know. I think I have something in the chat, and I don't know whether it's being directed to me. I'm going to read that now. Somebody said, is that supposed to say f of alpha in the? I don't get that. So maybe the person can actually simplify. Uh, you
Yeah,
know. Okay.
in the like when in the f of x it says 1 over beta raised to alpha, and then it's like an f without the like second line or whatever in the middle of it. F of, or I don't even know what that symbol is called.
Okay.
Like,
If you're talking, are you talking about this one?
yeah, yeah, with the thing in the numerator or the
Oh, the
denominator.
numerator.
Sorry.
Okay. Yeah, it's actually going to be 1 over beta raised to power alpha, gamma alpha, then x raised to power alpha minus 1, then
Uh,
exponential raised to power minus x over beta. So that is the formula.
Gotcha.
Okay, now what I'm trying, I introduced it to this the other time, and of course, if you this is the formula to find the mean, and of course the mean is just the product of the two parameters. The variance is actually going to be alpha beta squared. Okay, now and I said if you want to find the probability of any of a random variable s that follow gamma distribution, of course you need to have the parameters. Okay, but you know what, today I'm also going to show you how to do that. There's a way you can also do this in now. Okay, you remember the other time I solved this problem, and of course if you want to go through integration process, of course that may be tedious, and of course it can be done, but you know what, uh the essence of the lab. Now take a look at what I have here. Can you guys confirm if you're seeing that? If I see what I'm the calculation or calculating probability for gamma distribution in R, can you see that? Okay. Now take a look at the question. Find the probability. You want to find the probability of x less than 1, given that alpha equal to 2, beta equal to 0.5. Okay. Like I said, uh, you're going to write P gamma if you want to find the probability associated with gamma distribution. It's going to be P gamma. Okay. If you want to do the Weibull, it's going to be P Weibull. Okay. You remember when you were dealing with the normal distribution, it was P norm. Okay. Now we're talking about gamma now. Okay. You want to find the probability of x less than 1. And let me tell you this, the probability of x less than 1 is the same thing as probability of x less or equal to 1, because uh, we're talking about continuous random variable. Okay. Now you'll be given alpha to be 2, beta to be 0.5. Okay. I think what I'm going to tell you is this. In this course, okay, even if I don't say so, always take your alpha to be shape parameter and your beta is going to be scale. Okay, in this course, whether you are dealing with the Weibull or you are dealing with the gamma. Okay, now you specify that this is the code right now. Take a look at this guy here. This is the code right now to do that. One here, this is the one that we're talking about right here. Therefore, instead of you to, do you know that what we obtain right now, if you want to make use of the integration approach, it's take forever. Don't you know that? If you want to use this one here, okay, it's going to be, it's going to take so long. And that is the essence of the lab. You see, the beauty of the lab, you're going to get your result on time. Therefore, the probability here is 0.59, 39942. Okay. Now, if you want to solve another problem, what about the probability of s greater than 1? Okay. The probability of s greater than 1, you're just going to subtract all that from 1. You're done. What about probability of x lie between 1 and 2? Okay. For x lie between 1 and 2, you need to first focus on 2. Look at the one for 2. The P gamma for 2. You specify the parameter. Then you're going to subtract the P gamma for 1. Look at that for 1. The other one is for 1. Can you see that now? You see that now? Then whatever you get at the end of the day, you're going to subtract. When you subtract, that is the result you have. Now, please, if I ask you to solve a problem, then use R code. Use this. It's going to be so easy for you. Okay? You don't need to go through the rigorous mathematical, you know, the one I was walking you through the other time. Okay? So this is what you can do to achieve your, probability in the gamma distribution. Is there anyone want to ask a question? Is there anyone? Or can you guys confirm if you guys are hearing me clearly? Okay. Is there anyone that have a trouble time with what I just presented right now? How to find probability using the gamma distribution? Is there anyone? Whether you want to find the probability of less than, or you want to find the probability of greater than, or you want to find,
When would you
or
set
somebody,
tail
okay,
equal to false?
is that one?
When would you set tail equal to false? Like what condition?
That is it. The code right here, it has to be tail equal to true. Okay, that is the code right here. You mean this one?
Yeah.
So you have to use, it has to be, tail have to be true. That
Okay.
is the code, because the tail has to be true is because considering the probability of less than 1. That is a one-sided. You see what I mean? One-sided. If I'm considering greater than 1, that's another one-sided. Okay? So in the code, we're actually going to put true. Okay? Does that make sense to you now?
Yeah, definitely.
Okay. Now, the next thing that I want to talk about, now take a look at this. How do we find we want to find the value, we want to find the value y, so that the probability of y greater than small y is equal to 0.1. You know, what have we been doing right here? We've been finding probability value, right? That's what we've been finding, right? But what if in a situation whereby um, you are given a probability value, and they ask you to find, maybe something like that, okay? How can we go about that? In that situation, you are not going to be using a p gamma anymore, but you're going to be talking about quantile, okay? And quantile, that is q gamma, okay? You are not going to be using, and that is you're going to be using false. Now, somebody that asks about using true or false, this is where you're going to be using false. A chat came in now that I actually want to pay attention to. The person said, will the problem always tell us whether to use exponential gamma or Weibull? Yes. Uh, in the problem, we're going to tell you the distribution of the random variable. I think that's a very good question, because exponential, gamma, and Weibull, they perform the same function. And that is the reason why an examiner will actually tell you whether it is Weibull, gamma, or exponential. Does that answer your question now? The person that shot, does that okay? Okay, thank you for that. Now, you want to find the value here. You know the probability. If you want, and you are told that y actually follow gamma distribution with the shape 3.1 and scale 1. Okay, then you need to use a q gamma. Take a look at that q gamma, and you're going to write 0.1, the probability value. Then you're going to write the parameter. Then the lower tail, you're going to write false. Okay, this will determine the value of y, the quantile. That's what you're going to use. You are not going to use a p now. Okay, so that is what. Uh, is there anyone who want to ask question? Okay, somebody said, what if we want to calculate the probability of, you know, uh, x less than? Oh, that's a very nice question. Then you're going to do in that situation. Is that you change your tail? You're going to change your tail to true. Then, or you don't want to do that. Then you're going to subtract this from 1. Okay, Uh, so, but let me tell you, most of the time, what we do, uh, the probability, whether you want to find the probability of y greater than y or y less than y, it remains the same. Take a look at this. If I want to find the probability of, uh, probability of y greater than y, okay, I want to find the probability of y less than y. The file remain that I'm looking for y, okay, the file remain that I'm looking for y in the two. Okay, so whether you're looking for whether it is less than or greater than, of course, that is what you are actually going to have. Okay, so if that is the case, I want to go to another interesting distribution. But before I move, is there anyone want to ask question? I want to confirm if you guys are hearing me clearly. Are you guys hearing me clearly? Okay, now I want to go to another interesting distribution. All this y we've not really talked about. Uh, okay, let me check my chart. Can you please explain the answer to the previous question? Which previous question are you referring to? The example 4, or which one are you talking about? I'm still waiting. The person that said, can you explain the previous? Are you referring to this? Oh, uh, the probability of less than. Okay, in now the person is actually talking about the probability of y. Okay, less or equal to y. Okay, now this is what you're going to do if you want to find this. If the probability of y greater than that equal to 0.1, then this is going to be 0.9. Why do I get that? This guy here plus this guy here must be equal to 1. They are mutually exclusive. Do you understand that? Do you understand how to do that now? Okay, so what I'm trying to talk about, or let me see my chart. Okay, so what I'm trying to talk about is that if you take a look, give me 1 second. If you take a look at this guy here, he said the probability of y greater than y equal to 0.1. Okay, now what if the question has the result said y less or equal to this? Automatically, you're going to do 1 minus the probability of y greater than y, right? That's what you're going to do, which is going to be 0.9. Okay, then you're going to write your code for that. Okay, so the only thing that's going to change is just the probability that is going to change. You're still going to have your R code. Okay, but instead of you to specify 0.1, then you're going to specify the 0.9. Okay, because you know they are mutually exclusive. Okay, so I want to go into another topic, which I call another distribution called beta distribution. And let me tell you this: this distribution is the most flexible distribution in statistics, and I'm going to tell you why. Why it is the most flexible distribution. If you take a look at the Weibull and the Gamma that we just finished, they only have one shape parameter, one shape parameter. And let me tell you something. A distribution is flexible depending on the number of shape parameters in it. Okay. And you know what? Uh, if we want to model something that has to do with, what we've been modeling uh, up to this moment, we've been trying to model values in the real number, okay? When the random variable is greater or equal to 0. But what of in a situation whereby we are interested in modeling proportion, percentage, and of course, the random variable of that is actually going to be between 0 and 1. Particularly, I want to model the percentage of voters that will vote for a particular candidate, or maybe in a particular country, and in the airport, maybe at the border of the airport. We actually want to know what is going to be the proportion of the counterbalance that we're actually going to detect from the bag and luggages of those that are coming in into the country. Okay, and of course we expect the nature of the random variable to lie between 0 and 1. It's going to be a proportion. Okay, therefore exponential distribution cannot be used to model proportion. Gamma distribution cannot be used to model proportion. Weibull distribution cannot be used to model proportion, but what can be used to model proportion is beta distribution. And of course, uh, when I'm talking about beta distribution, I think I need to first define what I mean by beta function, because there's a difference between beta distribution and beta function. And we use beta function in beta distribution. Now, take a look at this. That's what we call integral definition of a beta function. For instance, the P and Q are the shape parameters. In beta distribution, the two parameters are shape parameters. But in Weibull and Gamma, it is only one that is shape parameter, the other one is a scale, okay, parameter. But here, the B of, what I just circled right now is called integral definition of a beta function, okay? Now, what I'm trying to talk about, if the two parameter, if alpha equal to 2 and beta equal to 3, how can I compute this? If I want to write this in integral form, that this is what it means: 0 to 1, then I'm going to have x raised to power, x raised to the power 2 minus 1, 1 minus x raised to the power 3 minus 1 dx. Okay? Anytime you see something like this is a beta function, this is an integral definition of a beta function. Okay? Now, we have integral definition of a beta function, and we have the non-integral definition. This is a non-integral definition. This is integral definition. This is what I mean, integral. Okay? Integral definition. Okay? And this is a non-integral definition. Okay? Non-integral. Okay? Now, if I want to do the beta p comma q, beta p comma q is actually going to be gamma q. Okay? Look at that, gamma q. Gamma p, gamma q divided by the gamma of the sum. Now, what am I trying to talk about? What I'm trying to talk about is if I have beta into 3 and 5, if I want to write it in the non-integral form, I'm going to add gamma 3, gamma 5 divided by the gamma of the addition, 3 plus 5. And this guy here is telling us the non-integral definition of a beta function. Okay? And if you take a look at this, I told you the other time, gamma 3 is going to be 2 factorial, gamma 5 is 4 factorial, gamma 8 is 7 factorial. Okay? Then if you simplify that, then you're actually going to have a result for that. Okay, now that is not where I'm going to. Where I'm actually going to is this. What is a beta distribution? Okay, what is the formula for beta distribution? That is what you have right here. And why am I dealing with the beta of the beta function of the integral and the non-integral the other time? Because of this guy here. Take a look at that guy here. You see that now? And this guy here. Look at that. Okay. So what I'm showing you right now, this is a probability distribution of the beta distribution of the first kind. Okay, we call it beta distribution of the first kind. Okay, because we have second kind, but only that in this lecture, I'm actually going to be focusing on the first kind. Look at the range of x lie between 0 and 1. Okay, so this is a distribution for modeling proportion, percentages. Okay, so now let us look at the shape of this distribution when we try to vary the parameters. Take a look at this. When p equal to 3 and q equal to 5, look at the shape you have. When you switch that, look at the shape. Somebody was telling me the other time whether we can switch parameters, even if they are shape parameters, and you try to switch them, it's going to, the curve is going to change. Look at this here. This is right. This is skewed to the right, but this is skewed to the left. Okay. So I'm just trying to tell you right now, if we want to model proportions, we want to model percentage, we need a more flexible distribution. Okay. And that is the reason why beta distribution is being used, because beta distribution is more flexible than Weibull. It's more flexible than gamma. Okay. For those of you that will be doing that will be going further in statistics in the future, of course, this beta distribution was derived from the combination of gamma distribution. Okay. The beta distribution that I'm showing you right now was derived through transformation, by trying to combine gamma distribution. But you don't need that, just for information. Okay, so take a look at that. When you vary different values of the parameters, you're actually going to have a different shape. And because of this make a beta distribution to be, the most flexible probability distribution in statistics. And you know what? We live in a world where things are changing. Of course, we don't need a rigid model. We need a more flexible model. We need a model that will capture reality. The fact remains, things are changing. These situations are dynamic. Then we need a dynamic model. When you make an attempt to use a static model to model dynamic situation, we are not going to get it right. And that is the reason why we need to be able to ask ourselves, researchers, we need to ask ourselves, the model we're using, okay, the model and the state of the model and the state of nature, okay? When the state of nature is dynamic in nature, you actually need to use the, a model that is dynamic. And that is the reason why we don't get things right at times in the world. things are changing. Then we need to use a model that is also, that is flexible. Okay, look at different kind of shape that I'm having here. Take a look at this guy here. That's a beautiful shape. We got some real life situation that look like that. We got some real life situation that look like each of those one. So which means if I try to play around parameters, okay, different values of parameters will actually give me different shape. Okay, and you know what I mean by shape? That is the shape of reality. Okay, there are different kind of shapes in reality, and of course, varying the values of parameters in a beta distribution, of course, can actually be used to figure it out. Okay, and of course, the beta distribution right here, apart from the fact that it's very useful in modeling uh, proportion and percentage, is also a prior distribution, that we use in Bayesian analysis. Okay, so you don't need that. You don't need that for now. Now let's go into an example. The proportion X of satisfied customers with a certain business follow a beta distribution, of course. That will follow a beta distribution because it is not going to be 100% of your customers that will be satisfied with your product. Okay, so if you are interested in the proportion of X, of course, that will follow beta distribution. Now, if you're giving the parameter to be 5 and 4, all what you need to do, take a look at this. If this is the distribution, you're just going to plug in the values of P and Q. When I plug in the values of P and Q, look at the distribution right now. Okay. Now, how do I obtain B of 5, 4? Of course, I told you before, you're actually going to go into the non-integral definition. Okay. What is the B of 5, 4? Look at that. The B of 5, 4 is going to be gamma 5, gamma 4 divided by gamma 9. You know what am I trying to use? The, the non-integral definition, or give me 1 second, the non-integral definition of a gamma of a beta function is gamma p gamma q divided by gamma p plus q. Here I'm using p and q. I can use alpha and beta. I can use whatever symbol that I want. Okay. Now when you do that, and I told you gamma 5 is going to be 4 factorial. Gamma 5 is the same thing as 5 minus 1 factorial, and that's why you have 4 factorial. Okay. So take a look at that. Then you're going to get this. Okay, the moment you get that, you have already obtained, this guy here. If you want to rewrite your f of s right now, you're actually going to write 1 divided by 0.00357 x raised to the power 4, 1 minus x raised to the power 3. Take a look at that. That is your new distribution now, after plugging in the value of p and q. Okay, and of course, are you guys still hearing me? Can you guys confirm?
Yeah,
Okay.
yeah, we can hear.
Oh, thank you so much. And of course, this is the shape. Okay. Now let me tell you this. Do you know that if I want to waste my time, you know, what did I use to obtain this? I use a non-integral formula. Look at what I got. Do you know that another way to do this, if I want to obtain, uh, I told you the other time, the integral definition is, that equal to 0 to 1, s raised to the power p minus 1, 1 minus x raised to the power q minus 1, the s. I can also use this to find what I obtain right here. But you're going to waste your time. Take a look at that. That's what I'm doing here. Oh my God, that's what I'm doing here. I'm still going to have the same results. Okay, so what I'm just trying to show you here is just how to use this is using the integral definition. But I want to tell you, if you want to save your time, I will advise that you go for the non-integral definition. That's going to be fine. You're going to be done on time. Okay, take a look at that. Okay, but if you use an integral definition, that is going to go forever. Look at that. Look at the step. Okay, and if you are not mathematically oriented, you're going to run into a problem there. Okay, so that is that. Let's say, for instance, this is what we want to find. Take a look at this. We want to find the probability that customer satisfaction is over 50%. If you want to find the probability that is over 50%, it means you actually want to find the probability of s greater than 0.5. Okay, and the probability of s greater than 0.5 is the same thing as 1 minus the probability of s less or equal to 0.5. Okay, do you know there's a way you can compute this in R? If you want to find, you are given, this is the question, this is what you're given the parameters to be 5 and 4, and you want to find the probability that customer satisfaction is over 50%. Of course, you want a situation whereby the customer, when you are producing or you are selling something, you want a situation whereby the customer satisfaction is going to be over 50%. You don't want it to be less than 50. What is the probability that that will be achieved? Okay. Now, what I'm trying to tell you right now, if you want to get that, then you need to first obtain the CDF. What is a CDF? Take a look at that. You're going to go from 0 to X. When you go from 0 to X, then what are you going to use right now? You're going to use this guy here. I'm going to show you now. You're going to use this guy here. Okay. And don't forget, we have already obtained the B of 5,4. F of S is going to be equal to 1 over 0.00357. X raised to the power 4, 1 minus x raised to the power 3. Now, this is what you're going to integrate from 0 to x. Okay. You're going to integrate that from 0 to x. And when you integrate this from 0 to x, what is your x? You're going to plug in a 0.5. When you are done, plug in a 0.5, then whatever you have, you're going to subtract from 1. But you know what? Uh, I want to tell you this. Uh, if you really want to solve that problem, you can make yourself be better. Okay. I'm going to stop my share right now. We have P of 5, P equal to 5, Q equal to 4. Now take a look at, I'm going to stop my share now. And I'm actually going to, oh, somebody just gave me something that makes sense now. In the chat, let me go to the chat. Something came in now. Somebody said it's going to be 1 minus P beta. Somebody said it's going to be 1 minus P beta is 0.55, 4. That guy is an excellent guy. Send a message to me for extra credits. Now I'm going to share with you what the guy actually proposed. Okay, I'm going to tell you now. You're going to see now. The guy said you're going to use 1 minus P beta. Look at that. P beta. Okay, you're going to specify your X. And the guy said then you're going to specify your parameter. And of course, in this case, uh, your S is actually going to be 0.5. And you specify parameters. So this guy here is is telling you the probability of S less or equal to 0.5. And of course, 1 minus that is actually telling you the probability of S greater than 0.5. So like I said, that guy is an excellent guy. Send a message to me for extra credit. Now, do you know that you don't need to go through the rigorous way of doing that? All what you just need to do, if the moment you know how to write a code, the word is fine. The word is fine. The moment you look, when we have kind of a complex problem like this, and we are looking for a way to solve a problem, and you know what, the solution to a problem should not be bigger than the problem, and that is the reason why anytime I have issue, anytime I'm facing crisis, do you know what I used to tell myself? I'm going to say, you know what, I'm bigger than my problem. That is the consolation that I used to give myself. Yeah, I'm bigger than my problem. Okay. And it is only when you are bigger, when you see yourself bigger than your problem, that you'll be able to solve your problem. If you are looking at your problem and you believe that your problem is bigger than you actually somebody can be overwhelmed by the problem. Don't be overwhelmed by the problem. See yourself as being bigger than any problem. And how do I see myself bigger than a problem? I'm going to get it. I'm going to have things done, but only that I just need time to figure things out. That's all. That's what I need. And the moment I'm able to figure things out, and if I want to figure things out, first I'm going to use the most simplest strategy in this world that work. Okay. Somebody said, is there a specific package now that we need to download in order to use the shortcut discussed today? Yes. You know what I'm going to do? Uh, I'm going to attach, the my TA will walk you through that in lab. But before the next lab, I'm going to send you a material. I'm going to help you to download the shortcuts that I talk about for different distributions. Does that make sense to you now? Does that make sense to the person that chat with me now that said, is there a specific package now that we need to download? Okay. So this is how you're gonna that is what you're gonna do. Okay. Now I'm gonna stop my share now, and of course, where we're gonna start next time on Friday. Uh, it's actually gonna be uh, we're gonna do fundamentals sampling distribution, which is a different that's going to be another topic. But let me tell you this chapter, what we're going to cover in the midterm too will be up to what we have done today. Okay. And you know what? Chapter 8 that we're going to start on Friday will not feature in midterm too. Are you guys hearing me clearly? Can you confirm if you guys are
Yeah, we
hearing
can
me
hear you.
clearly? Okay. Thank you for confirming that. So what I'm trying to talk about now is that the midterm tool exam is coming up. And of course, I'm going to have a preview, just like what I did in the midterm one. And you know what? What midterm two is actually going to cover is something that we do after the midterm one. Okay, up to today. Okay, that's what is actually going to cover. And what we're going to start on Friday, we're going to start a new topic on Friday that will not feature in midterm two. Okay, before I go today, let me tell you that uh, I want to have a quick review on probability distribution that we've done so far. Probability distribution can be declassified into discrete probability distribution and continuous probability distribution. Now, when you look at the discrete probability distribution, we cover binomial, we cover geometric distribution, we cover negative binomial distribution, we cover Poisson distribution. Another name for negative binomial distribution is Pascal. We call it Pascal distribution as well. Now, I quickly want to have a review before I go because I wanted to see the difference between each of these distribution. I could remember I started with binomial distribution, and of course, the binomial distribution is used, is a probability distribution of a dichotomous random variable, you know, so where there are two possible state of nature. Okay, I remember, for that, for binomial, and for we have what we call apogeometric distribution. We did apogeometric distribution, and apogeometric distribution also perform the same function with binomial, only that apogeometric distribution is used where we are sampling without replacement. Okay, from there we move to geometric distribution. The geometric distribution is actually telling us how many times am I going to fail in life, or how many times am I going to try before I'm going to have the first success. That's geometric distribution. Okay. From there, we move to negative binomial. The negative binomial distribution is a generalization of geometric distribution, because what the negative binomial is trying to tell us is that how many trials am I going to have before I started recording a good number of successes. Look at that. Then from there we move to multivariate apogeometric. Okay, in the multivariate apogeometric, of course, I show you how the population and the sample size can be partitioned. Okay, then from there we move to multinomial. Multinomial is an extension of a binomial distribution. In the multinomial distribution, of course, we are considering situation whereby the state of nature can be more than two. Then from there we move to what we call Poisson distribution. Poisson distribution is actually used. It's a distribution used to model the rare occurrence of an event, or something that occurs in a blue moon. And I told you that when the sample size in binomial distribution is large, okay, in such a way that the probability of success is 10 to 0, of course, you're actually going to use Poisson distribution. And of course, I also walk you through normal approximation to binomial. Okay, we use normal approximation to binomial in a situation uh, whereby you know we're dealing with a binomial experiment, but only that the sample size is so large, and that will be cumbersome to undertake. Because of that, we are because of tractability and simplicity, we're actually going to consider, uh, normal approximation to binomial. And finally, we focus on the probability distribution of a continuous random variable. We started from normal distribution. Of course, uh, if you want to use normal distribution, you need a mean. You need to be given the mean and variance. Okay. And don't forget, you need to standardize. Okay. So, and of course, I show you the shape and stuff like that. Then from there, we move to exponential distribution. Okay. Right from exponential to beta distribution, of course, an examiner is going to tell if, right from normal distribution to what we just finished right now, examiner is going to tell you. But in the discrete distribution, examiner is not going to tell you whether you are actually going to use geometric, you're going to use binomial, or you are going to be the one that will figure that out from the question. But for the case of probability distribution of a continuous random variable, of course, the examiner is going to tell you, okay, to, we have introduced it to exponential distribution, I introduced it to Weibull distribution, I introduced it to gamma distribution, and I introduced it to a beta distribution. And of course, I told you exponential distribution is used to model waiting time before the occurrence of an event. Okay, if I have a statistical component right now, okay, uh, as how long am I going to wait before it's going to stop functioning? Okay, of course, I'm actually going to I can use exponential distribution, I can use gamma distribution, I can use Weibull distribution. All these distributions are very, very useful in reliability study in engineering. And they're also very, very useful in survival analysis. Because in survival analysis, if a patient is being admitted to hospital, how long are we going to wait before this patient can be cured? Okay, that's a waiting time. Okay. And lastly, I talk about beta distribution. And I said the most flexible distribution in statistics is beta distribution. And this distribution is used to model percentages when random variable is a percentages or when random variable is a proportion. And that is the reason why you're going to have that line between 0 and 1. Okay. Uh, is there anyone? Oh, somebody said is uniform distribution included as well? Yeah, thanks for reminding me. Uniform distribution is included as well. I think I gave you the formula for uniform distribution, that f of s equal to 1 over b minus a. Okay, you have the interval, the upper interval is b, the lower interval is a. The example is when you look at the gas station where they sell gallons of gas. Okay, they know the minimum gallon they can sell. Okay, and they know the maximum gallon they can sell. Okay, and that is uniformly distributed. Okay, so what is the probability? You can using the interval, you can find the probability of having a particular gallon. So those are the distributions that we just that we discuss. I just have a review right now in case if there is anyone who want to ask question. Of course, you can actually meet with me, and like I said, uh, I'm going to help you with material where you're actually going to, that will be a straightforward code to all these distribution. You don't even need to do complex, rigorous computation. Okay, that is the essence of the lab. Is there anyone who want to ask question before I go today? Is there anyone? Okay, absence implies that you guys are good. Until on Friday that I'm actually going to come your way again, please make sure you stay safe and have a good day. Bye for now, guys.
Peace out.
Okay, go ahead. Oh,
I was just saying goodbye. Peace out.
oh, goodbye. Okay, thank you for that.